Here we are working with both linear and exponential decay. We've got the world's population of tigers in 1980. We're going to call that our starting point. And in 1980 we had 10,400 tigers. In 1990, 10 years later, we had just 7,960 tigers. So that gives us two data points. The question next says, if the population declined linearly, what was its rate of decrease per decade? So that means per 10 years. So I have 2 points, and I can make these 2 points 0, 10,400, and 1, 7,960. 1 because it asked per decade, and there's 1 decade between 1980 and 1990. Now I'm just after my slope. So the slope is the change in y over the change in x divided by minus 0 minus 1, which gives us negative 2440. So our slope is actually negative 2,440. The question, the wording on the question is, if the population declined linearly, what was the rate of decrease? So the rate of decrease was 2,440 tigers per decade. Next, it says if the population declined exponentially, what was its decay factor per decade? And again, I want per decade, so I'm going to use the same 2 data points over here. But now I have an exponential function. My initial population, or starting point, times my base raised to my exponent. My initial is when x is 0, so that's 1,400 times my base. Here I have my next data point is just 1 decade away, and it is 7,960. So now I have this equation, and I can use it to find the base by dividing both sides by 10,400. Turn on my calculator. Put in 7,960. Divide by 10400 gives me a decay factor of 0.765. It says for 3 digits, so B equals 0.765. It says round to at least, which means they would accept more decimals, but I have to have at least to 3 decimal places. So that's my decay rate. Now it asks for what is its percent decrease per decade. Round it to 2 decimal places. So this is the decay rate. This is the decay factor. The decay rate, I take 1 minus 0.765, and actually it asks for 2 decimals, so I know I'm going to need 3/8 there, and that's going to give me 1 minus 2, 3, 4, 6. It says to round to at least 2 decimals. The next number's 1 there. So it wants a percent. So this is going to be 23.46%. I couldn't round it to 3 decimals here because I needed this 4th decimal in order to get to that percent. And of course, in order there, I have to have this rounded. So we find when working with exponential functions, it's easiest to leave things in the calculator until we have to round at the very end. That's B. C. Predict the number of tigers in 2010 under each assumption, linear or exponential. Round it to 2 decimal places. I don't like rounding to 2 decimal places here because you can't have a fraction of a tiger. However, they didn't give us that option. So linear decay, I have a decay rate of 2,440 per decade. I have 3 decades. So I have to multiply by 3. 2,440 times 3. So after 3 decades, I'm going to have 7,320 tigers less than I started with. And I started with 10,400. So that gives me 3,080 tigers after 3 decades. For my linear one, I have a linear decay factor of 7.65. I raise that to the 3rd power, and I multiply that by my initial population, and I get 4,656.05 tigers. I would of course say just 4,656 because it is not possible to have a fraction of a tiger. Though of course this is only an estimate. Then we want the function, a function for the population of tigers, both linear and an exponential function. So a linear function, we are going to have L of t, linear function of time, our initial population, minus our decrease or our slope times our number of decades, where t is the number of decades. Our exponential function, e of t, is going to be our initial population times our growth factor of 0.765 raised to the t.